Swayam Prabha. Digital India. Educated India.
Friends, we shall be starting today one new topic on gradually varied flow, that is classification of gradually varied flow. In the last class, we have started the topic gradually varied flow, which is of course a very important topic of hydraulic engineering, and in many of our practical field activities we come across with this gradually varied flow topic. And today we shall be just trying to see, we shall try to see what are the different classification that we make to classify gradually varied flow. And before that, let us recapitulate what we did in the last class. We started with definition of gradually varied flow. Well, so we define what we call gradually varied flow, and then we gave some practical example where this gradually varied flow can occur. Like say in a river, if we give a barrier, then on upstream of the barrier we can get gradually varied flow, or suppose in a river or in a canal, if we put a sluice gate, then just on downstream of the sluice gate we can get again another type of gradually varied flow. Then in a channel, when flow is occurring and suppose there is a canal drop at a downstream end, there also we can have gradually varied flow. That way, for different situation we can have gradually varied flow. In those details we have discussed in our last class. And then we started with theory of gradually varied flow, that is how mathematically we can express the relationship of gradually varied flow. That means we can just see gradually varied flow profile as a water surface profile, and how we can derive a equation that will represent that particular profile. So that is what we call as a governing equation of gradually varied flow. So once we get this equation, then if we can solve that equation, then we will be knowing at what distance how much depth it is. With distance the depth will be changing, and once we get this governing equation, then mathematically we can solve that equation and we can understand or we can compute beforehand. Suppose in a practical field we want to do something and we want to know in beforehand that what will happen, that we can get. Well, and while deriving the governing equation, we should always remember, in the last class we emphasized on that, there is lot of assumptions we make. Several assumptions were made for deriving the gradually varied flow equation. So when we apply this equation for practical field, then we must be sure of ourselves that yes, we are applying this equation, we are solving for a gradually varied flow profile, for obtaining a gradually varied flow profile, but these equations has all those assumptions behind, and if those assumptions are not valid for that particular situation, then the computed result may have some amount of error involved. So that way, knowing the assumptions is very important, because then only we know limitation of our work. Well, and then we could see that the governing equation, this can be again expressed in different form. Well, when one form is advantageous for some of the computational work, another form may be more advantageous for explaining or for understanding some of the very basic phenomenon of gradually varied flow. So, that way we can have it in different forms, and with this understanding of gradually varied flow, today we shall try to see how we can classify the gradually varied flow profile. Okay. It is necessary to classify the channel bed. Channel bed is one basis of classifying gradually varied flow. Well, so let us classify channel bed first, and then we will go for classification of gradually varied flow in general. Well, we know that one slope we call as a critical bed slope. So, we will start with that critical bed slope. Critical slope. Well, what is critical slope? Suppose we write this as SC. Well, for a given discharge and in a given channel. So, for a given discharge in a given channel, for a given slope, we can have uniform flow at critical depth. That means, if we set the channel, in that particular slope, then uniform flow will occur at critical depth. So, uniform flow depth will become equal to the critical depth, and that particular slope we call as a critical slope. So, when we talk about critical slope, it is always related to a particular discharge, and of course, in a given channel we are talking about. So, that particular slope we refer as critical slope, where we get uniform flow depth equal to critical depth. That is, we can write that at SC normal depth Yn is equal to Yc. Now, if our slope, bed slope is less than that critical depth, then we call that slope as mild slope. So, if what is mild slope? Let us write here, mild slope is that when our bed slope SB is less than the critical slope. Bed slope is less than critical slope, means flatter than critical bed slope. Okay. Then that slope is called mild slope, and in a mild slope our flow depth, uniform flow depth will be greater than critical flow depth. Okay. So, we can write here that Yn normal depth will be greater than critical depth. Well, then we have a slope that we name as a steep slope. Okay. Steep slope. We did discuss about this before also. Again, we are just refreshing that, and we are going into some of the finer details of that. Then steep slope means when our slope, that is the bed slope, is greater than critical slope, and the greater means steeper than critical slope, and then we call that as a steep slope. Okay. So, SB is greater than critical slope SC, and when our bed slope is greater than the critical slope, obviously, suppose we are getting a uniform flow at a particular depth equal to normal depth, then when we increase our slope, normal depth will come down, means Yn will become less than the Yc. So, this way, these are three different slopes that we are getting: critical slope, mild slope and steep slope. And apart from that, we have two more slopes. One of course is horizontal slope. One is horizontal slope. Okay. Well, though when we say horizontal slope, in reality when it is horizontal there is no slope, slope is basically equal to 0. So, but still we name it as a horizontal, and then it is SB is equal to 0. Bed slope is equal to 0. Why we are defining it as a slope? Just to say, if someone asks that what is the slope, we say that it is horizontal, means slope is horizontal, there is no slopes, bed slope is equal to 0. Okay. And well, what will happen to the normal depth if the slope is horizontal? Well, that needs some discussion. Of course, we could have discussed that beforehand when we were discussing uniform flow depth, but okay, briefly let us discuss this here itself. If we write the equation of gradually varied flow, not the gradually varied flow, if we write the equation for uniform flow, then we got that is discharge say Q, that is equal to 1 by n and A r to the power 2 by 3 and S b to the power half, S b to the power half. And out of this part, that is on the right hand side, A r to the power 2 by 3, these are basically function of y, these are basically function of y. So, what we will get, that is from here, if we bring y, suppose that if I write as a function of y, then we can write Q is equal to 1 by n into function of y into S b to the power half. So, if I just try to find out S b, sorry, if I try to find out y, that is the normal depth y, which is remaining in this part, then what will happen? This is, say, this function of y we can express as q n then S b to the power half. Okay. Well, if we cannot separate out this part, then definitely we will be requiring trial and error procedure, but whatever that procedure may be, depending on the channel type. If it is a wide rectangular channel, we can get it very easily. Of course, that I will show you later, but say this being a function of y, we can see that if we put S b equal to 0, then this anything Q is the discharge and is having some positive value. So, this part divided by 0. So, that term is becoming infinity. So, well, and on the left hand side, of this part, that is here, we have other than this say sectional dimension like b, side slope z if it is a trapezoidal one, then we have n and other things remaining fixed. Suppose y n will remain on the left hand side. So, y n ultimately, if this left hand side is to become equal to infinity, this y n will have to become infinity. So, that way, of course, if we take a rectangular if we take a wide rectangular channel, then we can explicitly show that y n is infinity in this part. So, S b equal to 0 means anything by 0 that become infinity. So, normal depth become infinity. So, we can write that for horizontal bed, y n is infinity, y n is infinity. Well, and then we have another type of bed, that is adverse slope, Well, say when our channel is of the type that I am drawing here, say water is flowing in this direction and bed is having adverse slope in the opposite direction. Normally, our beds are always falling down in the direction of flow, and that is why water is flowing due to gravity. But many a time we can encounter in nature some slope where our bed slope is in adverse direction, means it is rising in the adverse direction, it is a rising slope and water is flowing on that. Of course, how water will be flowing, that is one point is definite, that although it is adverse slope, two-tail head on the upstream side must be greater than the two-tail head on the downstream side, and then only water will be able to flow. So, that part is there, but still the slope is adverse, and that sort of slope we refer as adverse slope. Okay. So, means when S b is less than 0, S b is less than 0, or we can write it in other way that S b is negative, S b is negative. And in case of adverse slope, there is another interesting situation about y n. So, for adverse slope, what will happen to the normal depth? Now, if we can see that this part, this equation again, if we see what I am writing here, that this function of y is equal to q into n divided by sb to the power half. Now, when sb will negative, then it is minus something to the power half, and square root of a negative value, square root of a negative number is, we know that it is a imaginary number. So, this right hand side become imaginary, and this become imaginary means our yn is also becoming imaginary. So, this yn is imaginary, that we can write for adverse slope. So, these two are the special case, that is for adverse slope yn is imaginary, normal drift, and for horizontal slope yn is infinity, yn is at infinity. Well, now with this basic understanding of different type of bed slope, now we need to go for another classification, that is and before going to classification of gradually varied flow, we need to classify, or rather we need to divide the flow zone into some specific zones. That is, flow zone means, say when a channel is there, then flow is occurring above the bed, and it can of course go up to infinity in that part. In this portion the flow is occurring, and this particular zone we divide into 3 different zones. Well, and when we will try to name the gradually varied flow profile, different type of gradually varied flow profile we will try to name, and when while naming those different type of gradually varied flow profile, we shall be requiring these zone name. First we will be requiring the bed name, then we will be requiring the zone name. So, let us first give the name of this zone. Well, now say if this slope is a mild slope, then what will happen? Say this line indicate critical depth line. That means, for a given discharge, critical depth in this particular channel, this channel I am just drawing here the bed line, but this will be having a definite section, and for that section, that is bed width or side slope z, whatever it may be. So, those we have, and for those we will be getting a critical depth, and that critical depth for that given discharge we call as a critical depth line. Okay. And if it is a mild slope, our normal depth line will be above the critical depth line. Say normal depth, uniform flow depth for the discharge is this much. So, that we call as a normal depth line. Well, so these lines, that is the bed line and the CDL, critical depth line, and the normal depth line NDL, these lines divide the entire flow zone into 3 distinct zones. So, the zone above the NDL we call as a zone 1. Now, there is one more important point that we need to mention. Say our NDL line will be above the critical depth line for a mild slope case, but for a steep slope case, our NDL will be less than the critical depth line. So, zone 1 is the zone above either NDL or CDL, whichever is at the top, That means, if I draw this as a mile, suppose this as a mile, and say if I draw another slope, it is steep, say okay, this is steep slope. If it is steep slope, NDL line will be here, NDL is here, NDL, and CDL will be above NDL, Then say for this steep slope channel, this will be zone 1, So, we should not confuse that zone 1 is the zone above NDL. This is not the statement actually. Zone 1 is the zone above either NDL or CDL, whichever is at the top. Okay. So, that we refer as a zone 1. Then the zone between NDL and CDL, that is the zone between normal decline and the critical decline, is called zone 2, is called zone 2. Well, similarly here also zone between CDL and NDL, that is called zone 2. And lastly, the zone between the bed and CDL or NDL, whichever is at lower depth. So, it can be CDL or it can be NDL, whichever is at a lower depth. So, this zone, that means this portion, is called zone 3, is called zone 3. So, here it will be zone 3, here this will be zone 3. So, like that, the entire flow zone above the bed we define as, we divide as zone 1, zone 2 and zone 3, zone 1, zone 2 and zone 3. And we are not giving in writing, but this figure, these two figure, this and that clearly define what is zone 1, what is zone 2 and what is zone 3. Well, and say now for some situation, if it is horizontal, if the bed slope is horizontal, if the bed slope is horizontal, then our normal decline will be at infinite distance. Now, if normal decline is at infinite distance, then where we will get a space above normal decline? We know that zone 1 is the space above normal decline, that is normal decline if it is at the top. Now, in horizontal slope, normal decline will be definitely at the top, but it is at the infinite extent or infinite distance. So, beyond infinity we cannot get anything, and that is why for horizontal slope there will not be zone 1, there will not exist zone 1. Well, that will define when we will be coming to further classification of gradually varied flow. Similarly, in case of adverse slope also, it is imaginary, so yn is not existing, it is, and that is why that zone 1 will not be existing there. Well, now with this understanding of different zone and with the understanding about different bed profile, bed slope, now combining these we can classify gradually varied flow profile and we can give name to these different gradually varied flow profile. So, we will be now going to gradually varied flow profile. So, let us take the first case, say our slope is mild, our slope is mild, that is mild slope, and by mild slope we means that SB is less than critical depth SC. Well, now when SB is less than critical depth SC, we know that critical depth will be lower here, CDL, and NDL will be at higher depth, normal depth line will be at higher depth. So, it is NDL. So, this zone is zone 3, this is zone 2 and this is zone 1. Now, if a profile, if a gradually varied flow profile occur at the zone 1, means on the top zone and on a mild slope, then we name that profile as M1 profile. That is, first classification we are making like that, when a profile, okay, that sort of profile we can have, suppose we are giving a barrier in this form and then say normal decline water was flowing either earlier like that, then it is gradually rising and like that, then this profile is named as mild slope and zone 1, M1. So, our first profile we are naming as M1 profile. Well, so M1 means the profile over mild slope and in zone 1. So, that is what the profile we will name as mild slope M1 profile, and of course, what will be the characteristic of this M1 profile, that we will be discussing later. Well, then we give another name called M2 profile. So, this M2 is, as you know, that if any profile occur over mild slope and in zone 2 this profile will be of course a drawdown profile like this, but that will be coming later, but this profile we name as M2. So, M2 is the profile over mild slope and in zone 2 and in zone 2. Well, following the same trend, if we get a profile in the third zone, that is in zone 3 and over a mild slope, then we name that as a M3 profile. Well, so lastly we are coming to M3 profile. So, that is profile over mild slope and in zone 3. So, that way over mild slope, if we get profile gradually varied flow profile GVF, we name it as, and if these are on zone 1, then it is M1, zone 2 M2, and zone 3 means it is M3 profile. Well, similarly, if we get, suppose our slope is steep slope, okay, it is like that. By steep slope we mean that SB, that is the bed slope, is greater than the critical slope SC, and in that case our critical depth line is, suppose this one CDL, then normal depth of flow in a steep slope will always be less than the critical depth. That will move with a high speed, velocity will be higher, but depth will be lower. So, normal depth is falling here somewhere, that is a normal depth line, and this is here zone 1 is this one, zone 2 is this one, and zone 3 is this one. Okay. So, these profiles are named as S1. So, by S1 what we mean, any profile lying in the zone 1 and over steep slope. So, this profile is S1. Any profile lying here in zone 2 and in, say, above a steep slope or rather over a steep slope, then it is called zone 2, and this profile will be a drawdown profile. This is a rising profile. That part will be coming later, just after completion of this classification, but let us see at this moment that this of course will be a drawdown profile, and then if a profile occur here in the zone 3, and this will of course be a rising one, that we call as a S3 profile. So, here we get S1, that is profile over steep slope, and in zone 1 and in zone 1, this is S1. So, what is S2 is profile over steep slope again and in zone 2. Well, then what is S3, that is profile over steep slope and in zone 3. So, that way we can classify the gradually varied flow profile occurring over steep slope again into 3 parts, that is S1, S2 and S3. Well, now we shall see that we could see if it is flatter than critical slope, then we are having 3 types of profile M1, M2, M3. If it is steeper than critical slope, we are getting 3 types of profile, that is S1, S2, S3. But if it is equal to critical depth, then what will happen? Let us see that. Well, suppose the slope is critical slope, that is critical slope. By critical slope, what we mean, that SB, that bed slope, is equal to critical slope. And as per definition, we know that by critical slope what we mean, that when uniform flow occur at critical depth, that means uniform flow depth and critical depth are equal. So here this is, say, CDL, critical depth line, as well as NDL, So here we have how many zones? Because we know that zone 2 is the zone between critical depth line and normal depth line. But here critical depth line and normal depth line are the same line. So we cannot have a zone in between that. And that's why zone 2 is not existing over critical slope. Zone 2 is not existing. Well, if we still want to name this as zone 2, then this will be just one line, and that line is the critical depth line or the normal depth line. And when we talk about classification of gradually varied flow, we cannot give a name to that, because this line is a uniform flow depth line. It is not a gradually varied flow. It is not varying depth. So this line, neither we can give a name to this zone, nor we can say this flow, if occurring here, is, say, 2 profile or something like that, because it is basically a uniform flow occurring in that line. Well, so here the zone 2 is vanishing, and what we have is that this is zone 1, and the flow profile, if occurs below these things, this is our zone 3, because 2 is not there, zone 3. Well, so when we talk about critical slope, over critical slope, we are getting 2 type of profile. One is called C1, that is again a rising profile like this, C1, and another is C3, that is also a rising profile. That C3 is also a rising profile. So that way we are getting 2 type of profile here. C2 is not existing. So C1 we call that profile over critical slope, and in zone 1, and C3 will be profile over critical slope and in zone 3. Well, so these 2 type of profiles we are getting. Well, then let us see what other sort of profile we can have. Say our slope can be horizontal, okay. Say it is a horizontal bed. So horizontal means SB is equal to 0, and over that, of course, we can draw critical depth line, CDL. If Q is known, then we can always calculate the critical depth. If it is a rectangular channel, Q is given, width is given. Suppose rectangular channel, then you can calculate Q square by Z whole to the power 1/3. That is giving us the critical depth. Well, and in trapezoidal channel also we can do it. Of course, it will require trial and error procedure, but anyway we can calculate critical depth. So that critical depth is the critical depth line. Fine. Then what about the normal depth? We have already discussed that part, that on horizontal channel, over horizontal channel, we cannot have normal depth. It will be the normal depth, if we say, that will be at infinite distance from the bed. So normal depth line we cannot have. We will say that Yn is at infinity. So now when we try to classify the zone, what we will do? Say this zone between bed and the critical depth or NDL, whichever is lower. Here definitely critical depth line is at lower. So, this zone we will name as zone 3 and the zone between critical depth line and normal depth line. So, anything above critical depth line, any portion, any space above critical depth line is lying between critical depth line and normal depth line, because normal depth line is somewhere at infinity. So, this portion is always lying between critical depth line and the normal depth line. So, as such this particular zone we will name as zone 2. Now, what about zone 1? Well, if we want to write here zone 1, then we will have to have something above critical depth, above normal depth. Now, normal depth here itself is at infinite distance. So, we cannot have anything beyond that, and that is why here over horizontal slope we cannot have zone 1. That is why we will be getting here two type of profile. That is, for to represent horizontal we write H. H represent the first letter represent the type of slope. Like that earlier also you could see that C represent critical flow and this second digit represent in which zone it is. Similarly, in steep slope S represent the slope and this 3 digit represent, or this 2 digit or 1 digit, this represent on which zone it is. Similarly, here M represent mild slope. So, first letter always representing the type of bed slope and the second digit is representing in which zone it is. Now, similarly, this H will indicate that it is over a horizontal bed, it is over a horizontal bed, and then if it is in zone 2 we will be writing H2. So, we can write this as a profile over horizontal bed, profile over horizontal bed, and in zone 2 and in zone 2, and in this 2 zone, second zone profile is a falling profile, that of course we will be discussing why, and this is H2. Then similarly, H3, that is the horizontal profile over zone 3, that we call as a H3 profile, and that is nothing but the profile over horizontal bed and in zone 3, that is we can call. Now, that profile will be a rising profile H3. Okay. Well, so over horizontal bed also we can have profile and gradually varied flow profile. Well, when we are saying as profile here, we are always talking about basically the gradually varied flow profile. So, we can have gradually varied flow profile over horizontal bed, and the flow profile occurring above horizontal flow, we get two type of profile, one is H2, another is H3. Well, and let us see if any more classification we can make. Well, that is again on adverse slope. Well, on adverse slope, if it is like that, so this is adverse slope. Adverse slope means our SB is negative, SB is negative, less than 0. Okay. Now, here also we can have critical depth line CDL, and that y and the normal depth will be imaginary, normal depth will be imaginary. Well, when it is imaginary, well, that will be somewhere here we do not know. So, we will be writing y and is imaginary, and as such, as we do not know what is there above critical depth where y and is, so here also just like horizontal slope, we will be getting zone 3 is here, and that zone we will be referring as zone 2, zone 2. And the letter that we use for denoting adverse slope, is A. So for profiles are concerned, we will be getting A2, that will be a falling profile like that. So this is A2 profile, and then there will be a rising profile in third zone that we call as A3 profile. Well, so A2 profile means profile over profile over adverse slope, and in zone 2. Well, now we can write another profile, that is A3, means this profile, that is nothing but profile over adverse slope and in zone 3. So now we can summarize that over different type of bed slope we get different type of profile, and so for classification of gradually varied flow profile is concerned, we classify it based on over what type of slope it is and in which zone it is lying. So that way we are getting M1, M2, M3, then S1, S2, S3, and then C1 and C3. C2 is not existing because over critical flow NDL and CDL, normal depth line and critical depth line, are at the same level. So we are not having zone 2. So we have profile C1 and C3. Then over horizontal slope we have H2 and H3. Here H1 is not existing. The reason is that normal depth yn is at infinite distance and we cannot have any other space above infinity, and that is why zone 1 is not existing over horizontal slope or horizontal bed, rather I would like to say. Similarly, we have A2, that is adverse slope zone 2, we have A2 and A3, and here also A1 is not existing. So these are the flow profile that we can have or over any type of slope, Of course, in nature, when we see the water surface profile, gradually varied flow profile, then say always we can get combination of these different types of profile. We will always get combination of these different types of profile. I mean, when we get combination, when the bed slope is changing from one slope to another slope, suppose horizontal bed is going, then it is converting to mild slope, then suppose a mild slope is changing to steep slope, then over different type of profile, different type of slope, we are getting different type of profile. So it will be a series of profile joining, and that way we are getting our flow surface, gradually varied flow surface. Well, so when we try to compute gradually varied flow, that will be coming in our next class. We will be discussing computation of gradually varied flow, and there basically we will be discussing how we can compute flow profile in those situations also. Well, with this classification of gradually varied flow, knowing the classification, now we need to discuss about the characteristic of these different types of gradually varied flow. Okay. So we will now go to characteristic of gradually varied flow. Well, and for that purpose, for discussing the characteristic of gradually varied flow, I have seen that it become convenient to explain its characteristic. Well, by characteristic what we mean? Characteristic what we mean that a profile, whether it is rising or it is falling, that is say one sort of characteristic. Then what will happen to this profile if we go to upstream side? That is, definitely in nature we will not get a profile for infinite extent on the upstream and downstream. Somewhere there will be a limit. Say uniform flow is coming, then it may get converted to a gradually varied flow. So at the upstream end, suppose uniform flow is coming and then it is becoming a gradually varied flow. At this junction, or say at the upstream of the gradually varied flow, what will be the characteristic of that particular profile, what sort of shape it will be, whether it will be of gradually rising type, or whether it is meeting a particular uniform flow line normally, or say asymptotically, how these things are happening, all those characteristics we shall be discussing. Well, and for discussing those characteristics, let us take the equation of gradually varied flow in a different form, means exactly not in a different form, we will be just taking a particular case, that is we will consider white rectangular channel, because for white rectangular channel the expression becomes simple and it becomes convenient to explain the different characteristic. Okay, so let us see how we can write the equation of gradually varied flow for white rectangular channel first. Well, we know that the gradually varied flow equation dy dx is equal to SB minus SF divided by 1 minus q square T by GAQ. That expression we all know. This expression we can write as, this implies, so dy dx is equal to, if we bring SB common here, then it becomes 1 minus SF by SB, 1 minus SF by SB and 1 minus q square T by GAQ. Now, these two terms, SF by SB and this q square T by GA cube, this term, these two terms we can express in terms of normal depth and the depth of flow, other depth of flow at any section, and this time we can define, this term we can define in terms of critical depth and a depth of flow of gradually varied flow. So, let us just try to do that first. Well, for a white rectangular channel, we know that, well, if we do not remember, let us just refresh that part. As it is a white rectangular channel, our B is much greater than y, say depth of flow is suppose y. So, what we can write, hydraulic radius R is equal to A by P, and this hydraulic radius A by P we can write as area is equal to B into y and perimeter is equal to B plus twice y. Now, if B is much larger than y, then this twice y, that is B plus twice y, in this expression we can neglect this twice y and this can be written as equivalent to B into y divided by B. Of course, this product we cannot neglect. For example, I said at the very beginning, suppose our bed width is 100 meter and in that 100 meter our depth of flow is suppose 1 meter or say 2 meter. Depth of flow is 2 meter and bed width is 100 meter. Then area is 100 into 2, depth of flow is 2 meters, so 100 into 2, that will become 200. So, we cannot neglect 2 here when it is in product form, 100 into 2 is 200. And so far perimeter is concerned, this is say B plus twice y, means 100 is the B plus 2 into 2, depth is equal to 2 meters, so it is 2 into 2, so this become 4. So, 104. Now, in place of 104 we can write as 100, that will not make much difference. So, that way we can write it as B into y divided by B. So, this part we can neglect and then this is becoming approximately equal to y. So, with this simplification, without creating much error in case of white rectangular channel, we can write the discharge Q is equal to 1 by n then A r to the power 2 by 3. So, area is equal to B into y, then in place of r to the power 2 by 3 we can write y to the power 2 by 3. This y is basically representing hydraulic radius. okay, this y to the power 2 by 3 and s to the power half. Now, when we are writing this expression for gradually varied flow, then we know that as it is gradually varied flow, at each and every section it will not be uniform flow depth. Rather, say if in a channel, if uniform flow is flowing like that, this is the yn, then somewhere here it will be rising like this. Say this is our bed and it is rising like this. So, at any section this will be y, depth y. It is not uniform flow depth, but it is uniform flow depth. And when we write this resistance flow formula, this is nothing but the resistance flow formula. We can write Say's equation, Manning's equation, all those resistance flow formula, and we consider this as valid. And if we remember, when we did a derivation for this resistance flow formula, basically this S value is coming as SF. It is the friction slope. It is the friction slope. That is, we are basically interested in finding the slope of the hydraulic head line, that is the total energy at one point upstream and total energy at the downstream point. If we join, then we get a line that we call as the energy line, and the slope of that energy line is basically SF, and that slope of the energy line actually govern the flow, because energy at upstream must be higher than energy at downstream, and then only the flow is occurring. So, this govern the flow, and that is why this slope is basically coming as SF. But when we talk about uniform flow, then we know the depth of flow is equal at every section. Depth of flow is equal at every section, and when depth of flow is equal at every section, velocity is also equal at every section. Now, velocity is equal at every section means v square by twice z, that is the kinetic head, is also equal at every section, and depth of flow equal means our pressure head is also equal at every section. So, total energy, slope of the total energy line and slope of the bed become equal. That we discussed at the beginning. Just to refresh that again, we are discussing that part. So, in case of uniform flow, our SF, that is the friction slope or the energy slope, is nothing but equal to the bed slope. So, in general, we can write for any depth, this is the expression, and of course, here we are making one assumption that the resistance flow formula is valid. That is why we are writing this equation, and then for, because discharge is same amount of discharge Q is supposed flowing here. Now, when we write Yn, then we can write 1 by n b y n, then hydraulic radius for normal depth condition is also y n to the power 2 by 3, and this we can write as b to the power half. Okay. So, if we write this as equation 1 and this as equation 2, then if we just divide 1 by 2, so dividing 1 by 2, what we will be getting, this is 1 is equal to, so this n and n is getting cancelled, b and b are getting cancelled, this is equal to y to the power 5 by 3, y to the power 5 by 3. So, we can write y to the power 5 by 3, and here it will be y n to the power 5 by 3. Okay. And then what is left is SF to the power half and SB to the power half. Okay. So, now again if we write SB bring this side, SF bring this side, and if we take square of this one, if we make square of both sides, then this expression we can write as, from here, let us write it here, this implies that SF by SB is equal to Yn